I think so. So, Alan will be talking about large-scale FFTs on GPU-based supercomputers with modern interconnects. So, Alan is a member of the technical staff at AMD. His work focuses on the design of FFT software for GPUs and high-performance computing systems. So, we have collaborated with Alan in the past on the Hefty application. Alan received his PhD degree in computational mathematics in 2018 from Sorbonne University from Paris, France. So, Alan, if you can hear us, please go ahead. Let's welcome Alan. Alan, you're on mute. Nat, do you have to unmute him?
There you go. Can you hear me?
Yes.
Hi. Thank you again for the invitation and for the
Thank
presentation.
you for making it, Alan.
So may I start now?
Yes. Do you want to make it full screen?
Yes. Is that okay?
Yes, perfect. Thank you.
Thank you very much. So good afternoon, everyone. My name is Alan Ayala. I've been working on FFTs for the past 7 years. And today I'm going to present about large-scale FFTs on GPUs, a survey on scalability analysis, how is it behaving nowadays on very big clusters, supercomputers such as Frontier, Summit, and El Capitan. So what we have scheduled for this talk, I'm going to talk first about a fast Fourier transform, what is it being used for in applications, and the state-of-the-art libraries, mainly those based on GPUs from NVIDIA, AMD, and Intel. Then I'm going to talk about some FFT implementations in parallel, the network topology and how this affects the scalability of FFTs, then some analysis on the effective bandwidth, and the impact of collective operations and MPI distribution on the scalability of FFTs, which is critical for nowadays applications running on large supercomputers. Okay, first of all, for those of you who are not very familiar with the FFT, this is an algorithm used for many applications in science and engineering. Pretty much all software kind of relies on the FFTs. And the FFT is an algorithm that was introduced back in 1965 by Kulitaki. Nowadays, and a paper on 2020 says the FFT is one of the top 10 algorithms of the 20th century. And essentially, what we are trying to do with the FFT is to solve this problem, to compute the discrete Fourier transform in a time that is reduced compared with the naive approach of computing the direct Fourier transform, which goes order of n squared. But if we use the algorithm for the FFT, such as the Kuritaki or the Bluestein algorithm, we can reduce the complexity to n log n. Essentially, we're doing a tensor product, as you can see here on the screen. We are trying to compute the vector or the array y using this summation. So with an input array, which can be an m-dimensional array. So essentially, the FFT and the algorithms that are built to compute the FFT exploit some particularities of this summation and reduce the complexity by a lot. So where is it being used right now, the FFTs at large-scale applications? We have software ranging from cosmology, wave propagation, and also there are some applications in machine learning. In the past, I've worked closely with Oak Ridge and the Department of Energy. We have had some applications from the exascale computing project. One of them is related to the cosmology simulation, such as HACC, where they use very big FFTs, up to 20,000 cube. A recent paper even showed that they can go over 30,000 cube. So these kind of FFTs require very large computing power and very large number of MPIs as well. And as you heard in the previous talk, this can be very challenging to scale MPI collective communication. And it's more important on the FFT side because it's a communication bound algorithm. As you will see now in the experiments and the analysis that I'm going to present, the communication MPI part of this is critical to continue scaling to more and more MPIs or devices, excuse me. And another application which is very important is on case-based methods, which is very useful in molecular dynamics. One of them is a software called LAMPS, which uses sizes over 1024 cube for many of their simulations. And also they use a large batch of smaller FFTs. So as you can see on the right, when they do their particle simulations, there is a considerable part which is related to the FFTs. We can have it, this simulation. And we see that it's very important that we can reduce this time that is taken for the FFT. And there are some other simulations in the industry that are also being increasingly interested on FFTs, which is reverse time migration for simulation on seismic 3D models. And there are libraries that are being developed right now for leveraging the power of MPI and GPUs. One of them, and according to a survey we did and benchmarking report that we have, the 2D Decompose and FFT library right now being developed by a group in the UK. They are supporting QFFT for NVIDIA GPUs, and as well as they are also adding AMD ROCm support. And they have been using MPI-aware communication, MPI code-aware communication, and they scale very well. There's a program written in Fortran, but they are also having an API in C++. This is one of the libraries that currently is having very good scaling results. ACCFFT is one of the first libraries that was created for parallel FFTs on GPU-based computers. So, but it's no longer being developed. Another one is QFFTMP from NVIDIA, which is showing very good performance results on petascale, and also right now running some problems in misprecision. You can get very interesting results when you combine a single precision with double precision. And well, I also wanted to mention in this library, which was one introduced in 2012, where they predicted how the FFT parallelization would go through exascale. Actually, their predictions went low because they thought communication were going to take only 40% of runtime when we have these exascale supercomputers. But nowadays we know that this can go over 90% because the GPUs can do the one or the local dimensional FFTs very fast. So everything goes through the network. There is some other libraries that I also wanted to mention, like FFT library, Japanese-based development, which is targeting mainly applications on particular problems in engineering. They have some limitations on the grid size on MPI processors. And FFT MPI library is one that's targeting specifically problems in molecular dynamics. It's written by the people who developed LAMPS. And they also are having support for NVIDIA and AMD GPUs. FFT library is one that I worked on for many years, that we added support for also for Intel GPUs to achieve a parallel library that can support multi-node GPUs. And there are a couple more that were recently introduced, MFFT, that exploit mixed precision for parallelization, and also sparsity on FFTs in the second one, SPFFT. So they are the main libraries that have been around recently for obtaining a parallel FFT. So essentially the algorithm that they follow, I try to summarize it in this slide. So when we have a grid of particle simulation, we can arrange our data to be in this kind of formats, like a bricks, that we call bricks or blocks, where they can be then transformed into pencil or slabs decompositions. So pencil is 1D geometries, and slabs will be the 2D geometries. So essentially, we decompose the problem, we compute local FFTs, taking advantage that the summation can be done also in multiple phases. We can do summations in lower dimension, and then do transposition, continue the other dimension, and so on. That is a feature from the FFT algorithm that we exploit in parallel. And that's what I've written here. Essentially, we take an initial shape of the problem, we compute local dimensionals in that direction, then we do the transposition, and then we continue the same process. So it's iterative process. If you have n-dimensional FFTs, you will go for more transposition, more local FFTs. And this part from line 10 to line 14, it's what many libraries have different names for this. They call it reshape, remap, or transpose. So depending on the library that you're looking at, they have different names for this part, and this is critical one. When you transfer data from different MPIs or different devices, you get a bottleneck on these lines, because the other part, when you compute the local 1D or 2D FFTs on the GPUs, this can take around microseconds or a fraction of a millisecond. So it's pretty fast compared with the MPI collective libraries that don't scale very well. Right now, the supercomputers, at least that we have in the US, have been focused mostly, their design have been focused on passing the top 500 supercomputing challenge, so which is not communication bound algorithms that are being tested. So there are also other supercomputers outside the US, for instance, from Fugaku in Japan, that focus their design mostly on tackling problems that have bottleneck in communication. And we're going to explore that from the topology of the supercomputers. So once we have an FFT in parallel, as I was mentioning, we can arrange them in 2D or 1D geometries, compute local FFTs, and then do the transposition step. So doing some math, we can arrange, as the previous speaker was telling us, we can have mathematical models that see how is the minimal or the maximum, or how to optimize the number of transfers for different kind of configurations. Here, for the slab case, we can parameterize that, given a number of processors, the latency of the machine, the precision of the problem, which is either complex double or mixed precision, the bandwidth of the machine, and also a number of processors. So the time to do a transposition when you have these 2D slabs is given by this formula. Similarly, if we arrange our data geometries in 1D or pencils geometries, we will have two steps of transposition. So we have the FFTs on the X direction, then on the Y direction, then on the Z direction, and two intermediate transposes. So the communication cost for this framework will be given by this formula. Again, it depends on the latency and the bandwidth and the number of processors. So once we have these mathematical approaches to compute the time for communication, we can also generalize when we have arbitrary types of bricks. So this is important for some supercomputers deal with this in a better way, because this gives you less messages. And the formula to calculate this is given like this. One library that has implemented the bricks approach is Swift, which is part of the hack program. So we have these three approaches. We can summarize on this table the communication time and how much is due to latency and how much is due to bandwidth. And we can also analyze which one would be better given a number of processors and the latency cost of the machine. And also for the bandwidth cost and the latency cost, we can compare which one or which will dominate. As we know, as we can see, the bandwidth and the latency at some point, according to the number of processes, will begin dominating the total cost. So we have developed some formulas for different architectures here. This formula here can show us the bisection bandwidth and for the communication type that can be slabs, pencil, or bricks. Here, for instance, for the Selenium supercomputer at NVIDIA, which has a flat tree topology, we have these different costs. And also we analyze the Fugaku supercomputer, which has a torus 6D network topology. We have obtained the bisection bandwidth. Some of you may be familiar with the bisection bandwidth. There's a brief explanation here. It is the minimum volume of communication between any two halves of the network, cutting a minimum number of links. So that's the definition for the bisection bandwidth. We have calculated for different topologies. And also we have calculated the communication time for the parallel FFT that it will take if we run with either of these decomposition types. Many libraries, for instance, FFT MPI or HEFT or ACC FFT, allows you to select the type of the composition. Most of them only support slab and pencil, which are the easiest to implement. But there are some few that implements also bricks like Hefty and Swift. Also at AMD, we have our library, Rock FFTMP, which supports the bricks decomposition. It's a general API that can give you a generic transposition in multidimensional space and is optimized for different topologies that rely on the AMD GPU network. So here I'm going to present now some results, experimental results using MPitch and MBI pitch in comparison to default implementations. For instance, on Summit, we have IBM distribution, which is called Spectrum MPI. And in Frontier, we have Cray MPI by default. And what we are going to show in here in this screen, we are comparing the different bandwidth obtained with different architectures, which different distributions. We can see that on Frontier, we have a theoretical peak of 100 gigabytes per second. The achievable peak, we can show it as well. And we can see that for small and big sizes, Cray and Pitch dominates when we can build the Open MPI. It doesn't give us much improvement with respect to the default one, which is supposed for the architecture. And here we have compared with our own build for MBI pitch on Spectrum MPI and also with Open MPI with UCX. And we noticed that for large FFT sizes, where the message volume on the all-to-all, or this was for all-to-all V actually, we can see that Spectrum MPI behaves well for all very big sizes. But as I was mentioning, many applications, what they do, they have a batch of small size FFTs. So this part here is important because when you scale, I will present large scale results later, almost 10,000 GPUs. So this part is very important. You get very small FFTs, and we notice that libraries by default, the distributions from Summit and Frontier, they don't behave very well with small sizes for FFTs, and that's where we had to leverage MBI pitch for these sizes. And also they have on the big scalability problems that I'm going to present. And before I do that, I also want to show some of the optimizations that we have been exploring in the literature. For instance, there are many libraries like FFTE, the Japanese-based one, which is entirely based on all-to-all, but they also have support for all-to-all V. As you may know, all-to-all has much more, has many optimizations compared with all-to-all V. And also, what we have observed also recently is all-to-all W, and as the previous speaker was showing, all gather can show some improvements if you do targeted or implementation. So what we have done was to explore all-to-all W in the sense we have coded some sequence of data shapes for the all-to-all W. So we have leveraged all gather and all scatter. And to see the comparison here, you can see that all-to-all V still behaves well, but this is because on this case, when we run on Summit, all-to-all W on the distribution, which is spectrum MPI, that is not GPU aware. So that is something that if you improve your network to leverage different sequences of data, like as I was showing on the previous slide on the implementation where we have the reshape. This reshape has 4 steps. Excuse me. It depends on the number of transposition involved in your case. Here is for pencil. It has 4 reshapes. But some of them will also need a local transposition. So the local transposition can be embedded on the on all-to-all W, and that's why this is a little bit higher, the time for all-to-all W, but it is saving us a local transposition steps, which can take up to 10% in many cases. So this is some improvements we have been looking at, and MPI pitch has been helping us also because they have a GPU awareness on that. And the impact of the GPU awareness is shown in this slide. As you can see, I'm comparing for different nodes up to 128, the different approaches, slab, pencil, and bricks. And we can see how it behaves for different, we are calculating the average bandwidth. We can see the difference of how it behaves for the non-GPU awareness and the GPU awareness. We have observed that we can leverage for different sizes, and this is part of a tuning framework that many libraries have. We have explored auto-tuning as well using tools from machine learning to select when it's more advantageous to use GPU awareness and when it's not. In libraries such as FFT, we can use a runtime flag to decide that as well. So it's very important to note that not always is a good idea to use the direct, for multi-node, the direct communication, but we can also leverage a master processor on the CPU to do the communication, and this will result in a better average bandwidth. Here is an experiment that we did for large scale using MBI pitch. We can see that here is for 6,000 GPUs, Volta 100 GPUs. We can see that at 6,000, the variation on the timing is higher. That's because distributions that don't deal very well with very small sizes. So when we run, and here we run 40 experiments and have done this plot, we can see that we don't get consistent results on timing. Can get even twice or more than the previous run. So that's something that it depends also on the distribution. Some distribution handle better the very small sizes at large scale. And as I showed in a previous picture, the one that we have been using for very small sizes on large scale nodes is MBI pitch, the one that behaves the best. Or scaling, it's not only to select the distribution and the type of algorithm, it's also important to leverage the grid of processors. So normally when we run experiment on MPI, we just give the number of processors and we tell the library, use this number of GPU per procs or distribute in this fashion. That's not enough. As you can see here, if you do bad selection of the grid size that you give for the FFT, it can stop scaling and stop its linear scaling. We have plot here for different sizes when you can decompose the problem, and 1024 cube problem, which is a very typical size in practice. And you can see that there are very bad selections that can make your problem stop scaling linearly, as we should expect in this log plot. And there are some others that keep scaling. So this is very important, and I think many libraries, some of multiple methods, or also the FFT, are looking into this. They are doing on the runtime compilation level. We can do some tuning and select, if user give us some, just the number of resources they have, we are tuning the number of, we are tuning the grid. So that's a step we have been recently working on our efforts. So to finalize, in this talk, we have presented large-scale effects of FFT in clusters based on GPUs, how they scale, and how is the spectrum for the state of the art. We have also presented some mathematical models and show some optimal communication lower bounds. And it is important for FFT scalability, as I was mentioning, to select the right decomposition approach, the right MPI communication, which can be a point-to-point, all-to-all, or you can mix them. And there are some libraries that do that, mix them, or you can also wrap up some of your local transposition into all-to-all W. So it hasn't been used a lot, all-to-all W, but recently it's gaining some interest because it can save us, it can help us move some of our work to the network. So in the literature, as I was showing, there are some approaches that can give you considerable speed up. According to, if you are many libraries right now, they're using just FFTs on CPU-based implementations. And right now, libraries I showed, they have easy to use APIs that can move and get us considerable speed up. And in Hefty, for instance, we moved a molecular dynamic library and we get 2.5 speed up, which was pretty good at the time. And also I've shown the importance of leveraging GPU awareness for MPI distributions. And yeah, I will conclude my talk with that. Thank you very much for your attention. If you have any questions, I'll be happy to answer.
Do we have any questions for Alan? If not, I think we are right about time for the break. So thanks again, Alan, for the nice talk. Sorry that you couldn't be here. So the next event for us will be the student poster presentation along with the coffee break, which will be held outside. So let's all head out for the presentation. And thanks again, Alan.
Thank you. Thank you all.